Okay, thank you very much. So yes, hello, thank you to the organizers for giving me the opportunity to talk to you today about my recent work alongside my collaborators in the Supersonic Project collaboration. I'm Claire Williams, I'm a graduate student at UCLA. And yeah, today I want to tell you about our high-resolution numerical simulations that we've been running using the Arepo code. So we have these kind of small box, 2.5 megaparsecs on a side simulations where we're trying to resolve the very early structure formation with POP3 star formation. And we run these simulations down to a redshift of 12. Our focus is to get a large number of these low mass gaseous systems, and we include the molecular hydrogen cooling to form the POP3 stars. Currently, we don't have feedback processes included. We're particularly focused on this baryon dark matter streaming velocity that we had a nice introduction to earlier today. So we have boxes with and without the stream velocity between baryons and dark matter at early times, and then we can compare kind of how these structures form in both cases. So in terms of the effects of the stream velocity, one of the things that it is known to do is to remove gas from its dark matter halo. So the stream velocity introduces a phase shift between the dark matter and baryonic perturbations at early times, and you can get things that I've shown in a cartoon up there, where your dark matter halo is offset from the center of mass of the gas. And in some extreme cases, you can even remove the gas component entirely out of its parent dark matter halo. So these supersonically induced gas objects, or SIGOs, are basically these dark matter-free gas structures formed through the stream velocity, and if they can form stars, they might contribute to the early globular cluster population. So my collaborator, William Lake, also a grad student at UCLA, has done a lot of work investigating these SIGOs, and he has some recent papers where the SIGOs are shown to form stars before falling back into like a larger protogalaxy, so then they would be kind of like a low metallicity star cluster on the edge of a galaxy. And that's what's shown here in the figures. He finds this gas cloud. The white circles are showing a dark matter halo nearby, and so it is totally dark matter free, forms stars, and then falls back into the halo. So these would be really cool signatures of the stream velocity in particular. But also, we're not just looking for these SIGOs. We are studying the broader population of dwarf galaxies in our boxes. So these are kind of the sites in the hierarchical model of structure formation. These are the sites of the first stars that form the building blocks for the buildup of galaxies. And I'm intriguingly showing a region of our box that is the same size as the source plane reconstruction for the Firefly Sparkle cluster. We're getting these amazing JWST observations of early, like tiny, small scale structure. And so we have this in our box too. If you are doing this type of observation, I would love to talk. So yeah, we have these star clusters embedded in gaseous filaments. We're observing that there's differences with and without this baryonic dark matter streaming velocity. And we have a large population in the box. So we can compile kind of overall statistics about the population of dwarf galaxies that will form in different regions of the universe. So we've found several kind of interesting effects. So the stream velocity can impact the morphology, the rotation of these structures, and also recently we showed that in regions with a high value of the stream velocity, star formation initially is delayed, but then as gas accretes onto structures, it will get shock heated and then cool quickly and have a strong burst of star formation, where you get this boosted UV luminosity from a strong burst of star formation, and this could contribute at the extreme faint end of the luminosity function, if not like a higher value than like increased scatter between different regions, because we know parts of the universe have a low value of the stream velocity, parts of the universe have a high value of the stream velocity. So potentially some really cool observables there, and I would be happy to, I know we don't have time for questions, but I'd be happy to talk about all these different effects and the research that we have done at one of the breaks. So thank you very much.
Thank you.